Good evening and welcome to tonight's talk with astrophysicist Kathryn Johnston. Welcome to the Milky Way, Gaia, the galaxy, and you. We are delighted to have you all joining us tonight at the Stavros Niarchos Foundation Library. My name is Jackie Trailis, and I am a member of the programs team here at SNFL. Before we start, I would like to thank the Stavros Niarchos Foundation for making programs like this evening's possible. I would also like to thank the Columbia University Astronomy Department for all their hard work helping us bring this first astronomy event to our rooftop in Midtown. I would like to remind you that if you don't already have a library card, it is easy to get one by visiting any information desk in this building. Finally, I would like to encourage you to visit NYPL's website and take a look at upcoming 7 Stories Up programs like this one. We have an excellent lineup this season featuring new fiction, nonfiction, music, local history, and more. We would love to have you in this space again. Now let me introduce tonight's speaker. Kathryn Johnston is an astrophysicist interested in understanding how galaxies form, are structured, and evolve, with a particular emphasis on dynamics and interactions. She pursues this goal using a combination of close collaborations with observational colleagues and computer simulations of galactic collisions. She arrived in this field following an undergraduate degree in mathematics from Cambridge University, a PhD in astronomy and astrophysics from UC Santa Cruz, and a postdoctoral position at the Institute for Advanced Study at Princeton. She joined the Columbia Astronomy Faculty in fall 2006 after spending 7 years as an assistant professor at Wesleyan University. Without further ado, please welcome Kathryn.
Hello, everybody, and welcome to the Milky Way. I do specialize in the Milky Way galaxy, so I get to say that, welcome to the Milky Way. But before we start, and I am going to tell you today about some discoveries that astronomers have made in the last decade about our home galaxy in particular. Before we get going, though, I wanted to issue you a general invitation from Columbia University Astronomy Department, and in particular from Amanda Quirk. Amanda, can you wave? Amanda Quirk is our outreach officer, and she runs for us monthly talks like this and viewing from the roof of our building. And we would be delighted if you came and visited us. In particular, in the last few years, unfortunately, we've had severe shutdowns. You may have heard about it in the press. And we would love our neighbors to come and see us. So please look that up on our website. OK, so to get going, welcome to the Milky Way. Let's start by reminding ourselves what a galaxy is. And this is an artist's impression of what the Milky Way looks like. And so you can see, what you see is a vast collection of stars and gas and dust. And what you don't see is that this vast collection of stars and gas and dust is actually surrounded by a much bigger collection of dark matter, that mysterious substance that is around us in the universe. And that dark matter for the Milky Way that's associated with the Milky Way would fill beyond this auditorium. We're not going to talk about that today. We're going to concentrate on the matter we can actually see. And you can see here, the sun does not sit at the center of the Milky Way. It sits partway out in what's called the disk of the Milky Way. And within that disk are these beautiful spiral arms, all encircling a center, which has a rather linear structure. And we would call that the galactic bar. If we turn the Milky Way on its side, you might see it something like this. This is actually our nearest neighboring galaxy, large nearest neighboring galaxy, the Andromeda galaxy. And you can see here, there's less of a bar structure, more of a bulge in the center. But it gives you a sense of what this disk of stars might look like more on. So overall, we can say that these big spiral galaxies, there are other types of galaxies in the universe, but maybe about 30% are spiral galaxies like our own Milky Way. We can describe them loosely as flying saucers in shape. Okay? Now we're going to do the testing part. If you fail the test, you have to leave the auditorium. Just kidding. It's a popularity contest. Let's think about how big the Milky Way is. So what we're going to do is imagine we take the sun, and we're going to put the sun in the palm of my hand here. And we're going to take a vote. Where do you think the next nearest star would be if the sun is the size of a baseball? Okay. Would the next nearest star be in this room? Would it be in Times Square? Would it be in Paterson, New Jersey? Or maybe, would it be in Houston? Okay, so we'll label these 1, 2, 3, 4. Who votes for 1? 1 vote for 1. Yay! Who votes for Times Square? Another vote for Times Square. Who votes for Paterson? Yeah, a bunch. That's a technical term. A bunch of people voting for Paterson. How about Houston, Texas? Yay, that's everybody else. And everybody else is correct. But take a minute to think about it, right? This is the sun. It's this size. The next nearest star, roughly the same size, is in Houston, Texas. That's a lot of empty space. That's why we call space space, right? OK, so the galaxy is huge. The next nearest star is in Houston, Texas. This is a galaxy rather like our own. And you can't even see the individual stars because they look so close. But they're actually separated by vast amounts of space compared to their sizes. OK, let's try one more. Aha. OK, so we all know that light moves really fast, right? It moves at light speed, OK, which is about 300,000 kilometers per second. So you snap your fingers, and light moves 300,000 kilometers, right? So how long do you think it takes for light to reach us from the center of the galaxy? So on this galaxy, the sun, say, would be out here. How long does light take going at 300,000 kilometers per second to get from here? OK, so you've got the drill. Who votes for 90 years? 1, yay! 1,700 years. Nobody. 24,000 years. OK, a bigger bunch. Another technical term. 1.3 million years. OK, so the bigger bunch, 2 bigger bunches. But it's actually 24,000 years. I'm being very tricky on this one. 24,000 years, but that's a long time, right? So this gives you an idea. When I say the Milky Way is very big, it's very big. If you learn nothing else, this talk, the Milky Way is very big. OK, the other thing is we're used to seeing these gorgeous images of galaxies. If we went back and took that image tomorrow, it would look pretty much identical. If we took it back, took an image in 100 years, it would look pretty much identical. If we took it in 1,000 years, it might still look identical, right? However, the stars actually are in constant motion. So in fact, if we look, we can measure how fast things are moving, even though we don't see the stars move during our lifetimes appreciably. So we can actually tell that these spiral galaxies are slowly rotating over the lifetime of the universe. So we can actually say these flying saucers are spinning at the same time. Okay? So we have a couple more of these here. Oh, I'm going the wrong way. Let's try this again. No, we're still going the wrong way. Maybe I missed. OK, the sun moves at what speed as it goes around the galaxy? So the galaxy is spinning. How fast do you think the sun is moving? So take a minute and look at these numbers, right? 1 meter per second, 4 meters per second, 7 kilometers per second. A kilometer is about 0.6 miles. 250 kilometers per second, 350,000 kilometers per second. Let's vote. Who votes for 4 meters per second? Anybody? Excellent. 7 kilometers per second. Nobody. OK, I'm giving away my strategy. 250 kilometers per second. OK, and this is a bunch, not a big bunch by my estimate. Good. 350,000 kilometers per second. Great! You lose. Because the answer is 250 kilometers per second, which is not a small number. It's not as big as 350,000. But actually, I had mentioned that light moves at 300,000 kilometers per second. So actually, Einstein would tell you that it would be impossible to go this speed. Einstein says nothing moves faster than the speed of light. So that's how you could have ruled out that answer if you remembered Einstein and the number I said a few minutes before, right? So anyway, 250 kilometers per second is not to be sniffed at. I want you to take a second, literally, to think about it. See if I can do it this time. We just moved 250 kilometers. Why? Because the sun has moved 250 kilometers around the galaxy in that space of time. In fact, since the beginning of this lecture, we've moved thousands of kilometers, right? Because of the sun's motion around the galaxy. Okay. So the galaxy is really big, and the sun, however, is moving really fast. We're going to do one more of these. So we've got the galaxy is really big, and the sun is moving really fast. How long do you think it takes the sun to go once around the galaxy? So it completes one orbit. Okay. So just take a minute. Yeah, it goes around in a circle around the galaxy in the same way. You can think of it like the Earth going around the sun, but on a much bigger scale. No, no, no. We sit outside. So we're thinking about a star here. How long does it take to go once around and get back to where it started from? It's moving 250 kilometers per second. Okay, votes for 10,000 years. 1, yes. 2, sorry, I missed you. 5 million years. Okay, a pretty big bunch. 250 million years, about the same. Okay, so I'm shaking it up. It's 250 million years. 250 million years, that gives you an idea. It's moving 250 kilometers per second. But the galaxy is so big, it takes 250 million years just to go once around. So another fun thing to think about is, say that this red point is where the sun is. This is where the dinosaurs died out 65 million years ago. The sun was over here. And that kind of gives you a sense of scale. OK, good. But the take-home point from this, there are 2 take-home points. One is the galaxy is big. The other thing is, despite the fact that we get these gorgeous images that won't change their appearance during their lifetime, dynamics is everywhere. The universe is very dynamic. Stars are very dynamic. Things are in constant motion at actually incredibly high speeds. So now let's get on to what we're going to talk about today, which is a mission. The results, a lot of what I'm going to tell you about is informed by a satellite mission from the European Space Agency called Gaia. And its mission sounds incredibly boring, because its mission was simply to measure the position of every star it could on the sky with better accuracy than had ever been done before. And that's where this term comes from. It's a branch of astronomy. It's called astrometry, measuring positions of stars on the sky. Okay. And one of the wonderful things about the Europeans is they gave the world the data. So since every few years, the European Space Agency releases all the data that it's got on the Milky Way, on stars in the Milky Way. And then astronomers all over the world scramble to analyze it. It's really fun. And this is going to be, you're going to see the result of that. So what I'm going to do for the next 10 minutes is show you a video, a visualization with some of the Gaia data in it, made by Jay Steiner, who was a senior a few years ago at Columbia. And this video, we're going to start here. It actually starts not with the Gaia Space Telescope. It starts with NASA's own Hubble Space Telescope, also a gift to humanity, this time from the Americans, because international teams of astronomers can propose for Hubble Space Telescope time and James Webb Space Telescope time. And so science is this global community. So Hubble was launched in 1990. And since that time, it's been orbiting the Earth. It goes around the Earth about once every 90 minutes. And you can see it here. It's looking deep, deep out into space, into the vast reaches of the universe, and reaching far, far out. At the time, Up until JWST was launched, it was seeing the most distant galaxies we'd ever observed. Hubble's not alone up there. What you're going to see in a minute, JACE takes us outwards, and they show us how Hubble is orbiting the Earth. In this visualization, you'll be able to see the orbit of Hubble coming in. And then you'll also see orbits for all the other man-made satellites that are out there with Hubble. And it's really quite crowded. As you move out, you're going to see these coming in. It's really quite crowded out there. And there's a set that are quite close to Hubble's orbit, and there's a set that's further away. But if we zoom, these are all man-made. If we zoom out far enough, of course, we actually get to the natural satellite of our own Earth, which is the moon. It should be coming in any second now. And the moon sits about 1,000 times further away than Hubble does from our surface, at about 300,000 kilometers. Oh, no, sorry, 300,000 miles. So here's the moon. Now, what we're going to do at this point is we're going to go back to 2013 in December. It was a special day in 2013 in December that the Gaia satellite was launched by the Europeans. And you should see it coming off from the Earth. There'll be a green streak coming off from the Earth. Here we go. We've gone back to 2013. There'll be a green streak coming off from the Earth. And you'll see that it goes out, way beyond the Earth, and actually beyond the moon to a point outside the Earth's orbit, which you should just be able to see here, coming out here. This is Gaia coming out in December 2013. And it's been sitting out there alone in space until JWST joined it, because it's also at the same point, or close to the same point. And this special point is actually on the opposite side of the Earth from the sun. So you could say it takes an entire year to orbit the Earth, because it always stays on the opposite side of the Earth from the sun. It's a particularly stable point in space, which is kind of fun. And it's a great place to be because you get a pretty pure view when you have the mission of trying to measure positions of stars on the sky. OK, so if we talk about that for a minute now. So Gaia's mission, as I said earlier, is to measure positions of stars on the sky. Historically, this is something that humans have been doing for millennia. So if any of you caught that, I was circling a constellation that may have been familiar to some of you. It's called Orion. So you can kind of think of our ancestors in their way of labeling stars in constellations and grouping them in constellations. That is a way of measuring their positions on the sky. So in a way, astrometry is the most ancient branch of astronomy. And of course, the exact constellations that you choose vary on your culture. And so these groupings are the ones from Roman times and Western culture. But there's nothing particularly special about those groupings. Other cultures will group the stars in different ways. So Gaia is measuring these positions really well. We're going to find that there are two things that we can get from those positions. But first of all, to give you a sense of accuracy of Gaia, imagine you are on Earth, which you are. The more difficult part is imagine that I'm on the moon. And I'm on the moon. You're going to see me in a minute. And I'm not to scale. The moon's actually too small. And I'm waving at you, right? So I'm waving at you like this. And I'm glowing very brightly. That's important, because otherwise you wouldn't see me. But if you were Gaia, I was glowing really brightly. You had eyes as sensitive as Gaia. And I was on the moon. You would see me waving. That's how well Gaia can measure positions on the sky. That gives you a sense. A second example. Suppose I was also very bright, and I was walking around the next nearest star to us, not the sun, the one 4 light years away. And I was walking about just normal walking pace, maybe New York walking pace, right? I was walking that fast and glowing brightly. If you had Gaia eyes, you would be able to see that motion. So Gaia can detect humans walking around the next nearest star. Well, that's not the main point. It could if they were there. We haven't noticed any. But more to the point, it can measure, remember we said, It's hard to detect the motion of stars during your lifetime. Well, Gaia is able to detect the motions of stars in our galaxy and measure them. And the second thing it can do is actually also, by measuring the positions very carefully, it can also measure distances to stars, which is incredibly difficult. So the video got ahead of me here, but what I was trying to show you there, these are the stars in the constellation of Orion. And you can see if you look at their true positions in terms of distances from us, their true positions in space, it's not a cluster of stars, which many of you may already know. Like the constellations just happen to be aligned along stars that are aligned along our line of sight. And so we've known for many millennia, well, I would say centuries, that the, no, maybe it's not centuries, maybe a century, that the distances to stars in Orion are such that it's not a cluster. But the thing about Gaia is that it could do that for stars that we see, and then it could do it for the millions of stars up there that are too faint for our eyes to see. So these are the amount of stars, the density of stars that Gaia actually sees. And this is how it's seeing those stars moving. So what you're actually doing now, Jace is having a lovely fly through. These are real stars whose real positions have been measured and whose motions have been measured by Gaia. So this is really the Milky Way. If you lived for a few 100,000 years and you could fly faster than the speed of light through it, okay, which is really fun. And the video's got ahead of me again, but what the last part of this video, this was showing you the sorts of measurements that Gaia made. In the last part, Jace zooms out, so that imagining we can see the whole Milky Way. And the white points here are some very distant stars. You can see they're outside of the Milky Way, but they don't seem to be randomly spread in space. In fact, you can kind of see this clump of stars, and then it looks like there's streams of stars ahead and behind the clump. And that's actually a technical term. I work on streams of stars. And this is a set, this clump is actually an entire other galaxy that we have known about for a few decades. And Gaia has measured the motion so we can see how we expect this entire other galaxy to move and those streams of stars to move in the future. So since that's something I've been working on for a while, we're going to pick up from here. So what I hope I've given you a sense of is how scientists worldwide have been able to use a satellite to actually measure the positions, distances, and velocities, speeds of billions, actually. Gaia's catalog contains billions of stars in the Milky Way. And from that, I'm going to tell you a few things about what we've learned about the disk. But we're going to do a bit of a sidetrack first, because I want to talk about those streams, because it's something I'm a specialist in. And what we want to understand, right, is where those streams come from. So this is a scientific animation. What I mean by that is you can see faintly, this is a cartoon edge-on of the Milky Way. This started off as a ball of stars at the beginning of the video. And what we've put here to make this scientific animation is we've put science in to predict each frame of this movie. So you don't have freedom to make up the frames of the movie. In this, what we've done is I'll run it one more time. Here's the ball of stars. And we've put in Newton's law of gravity and motion. And as the ball moves around, it becomes pulled apart by immense forces from the Milky Way. And the forces are such that they actually pull stars off of this separate galaxy, and they start destroying it. So some people like to call this galactic cannibalism. This is the Milky Way eating up one of its neighbors. This is called, the one we saw is called the Sagittarius dwarf galaxy because it's observed in the constellation of Sagittarius. It was discovered in 1994. Okay, so what is going on here? And I actually already gave you the answer. Gravity, right? It's the gravitational forces between the Milky Way and the dwarf galaxy that are pulling it apart. The closest thing that's exactly analogous to this are tides on the Earth. You know, you're always told, oh, the moon causes the tides on the ocean. This is because the moon, here's the moon sitting here, I'm the Earth, and here's my ocean, right? This side of my ocean is pulled towards the moon at a slightly greater force than this side. So that means the ocean bulges towards the moon. And in effect, you've got to bulge this side because the Earth is pulled at slightly greater force than this side. So you have the Earth being stretched by tidal forces due to the gravity of the moon. So if we think about that picture, we can apply it to this satellite. The Milky Way is pulling this side of the satellite with slightly greater force than this side of the satellite. And that means it stretches the satellite, and that causes these stars to be lost from the satellite. It's the same physics. That's what's beautiful about astronomy. You can take the physics that we learn about on Earth, and we can apply it to an entire other galaxies. They even have the same name for the physics, tidal forces, the same tidal forces that are working on the Earth. But anyway, if you haven't thought about gravity for a while, I have a joke. There's one joke, so I'm warning you it's coming up so you can be polite and laugh. And I like to say that I've invented a new type of therapy. It's called gravity therapy. I'm going to start marketing it soon. And it basically comes about, I'm actually trying to recruit you all to be gravitational dynamicists. In some ways, it's a really great job. If I've had a terrible, terrible day at the office, happens all the time. Columbia is a tough place, as you may realize from reading the newspapers in the last year. I go home, and I open the fridge, and no, wait a minute. No, there's a step before that. Wait a minute. Take your notebooks out. Step 0, go home. Step 1, look in the mirror, and you can say to yourself, and I know this as a gravitational dynamicist, Kathryn, you are very attractive. And why am I attractive? Everybody on the planet is attracted to me. And you can all say that, okay? Gravity therapy. Second step, go to the fridge, open the fridge, get out that chocolate cake. I have it always at home. I'm sure you do too. Get out the chocolate cake, eat a big piece. Then you go back to the mirror, and you look at yourself, and then you can say, and now you're even more attractive. Because you're more massive, right? More massive, thanks higher gravity. Okay, so that's gravity therapy. It's a practical way of staying happy every day. And it also reminds you how gravity works, right? So it's the force, mutual force between massive objects. The mutual part is going to come back in a bit. So far, we've learned about the dwarf galaxy being ripped apart and cannibalized by the Milky Way. Okay, so now let's get back to the disk of the Milky Way, the main business. I wasn't really here to talk about dwarf galaxies. So we said that spiral galaxies are flying, spinning sources, right? So let's look at what Gaia, actually, if we look at all the billions of stars in Gaia, this is not an image, this is a cartoon, remember? But if we look at the billions of stars in Gaia and we try and plot what those stars are telling us about how this disk is moving, they've come up with something quite interesting. I'm going to overlay it. At first, you won't be able to see it very well. But what I'm going to show you is a graph, and it's overlaid here to show you the center of this graph. That's where the sun is going to be plotted. And as you look towards this part, you're looking towards the center of the galaxy. It's on the same scale. And the red patches of the graph show you bits of the galaxy that are going up. And the blue patches of the graph show you bits of the galaxy are going down. So you can kind of see there's a red patch here. This part of the galaxy, the disk is going up. The blue part, the disk is going down. The The red part, the disk is going up. The blue part, the disk is going down. So that's showing it with the colors so you can actually see it much better. And the point that you see here is actually, what did we expect? What we actually expected is, I had talked about the stars going around in the disk. We talked about having a flying saucer. I didn't talk about the disk doing this, right? This was something we've discovered in the last decade or so. It was a little bit before Gaia we started to get hints of this. But Gaia was able to show us that we actually have ripples in the spinning saucer. So we have a flying saucer that's spinning, and it has ripples in it. So this is very much a cartoon. It doesn't look as exaggerated or as clean as this, but this gives you an idea of what we're actually seeing in the disk of the Milky Way. And the sun is this yellow point here. Okay, so we get back to the same questions. These are the questions. My favorite part of this is actually this, figuring out why. Like, what is going on? How could this happen? How could the spinning disk be rippling? And the answer actually goes back to this fellow, the Sagittarius dwarf galaxy. We said gravity was mutual. The Sagittarius dwarf galaxy is being ripped apart cruelly by the Milky Way and will be destroyed, we imagine, in a few billion years. But actually, the Sagittarius dwarf galaxy itself, its gravitational field is influencing the galaxy. So now I want to show you another animation, this time, where we actually ask not just how the Milky Way is influencing the Sagittarius dwarf galaxy, we've also asked, how does this object influence the Milky Way? And if you watch it come up now, you can actually see where those ripples could be coming from, right? Because gravity is mutual, it can actually cause galaxies like ours to ripple, to warp, to flail around, okay? And we can actually see that in the data from the Milky Way today. Okay. I'm going to play this one more time because why not? Yes, absolutely. Yes, things are moving at different levels and speeds. And actually, that's an entire other project. And if this talk was actually another half hour longer, I would tell you about that too. So you'll just have to invite me back because I'm an egotistical megalomaniac. Anyway, so this video, I also have to advertise, this was made by another one of our excellent graduate students, and not graduate students, undergraduate students, Andy Sanidakis. He was doing a visualization of a simulation run by one of our researchers, Shervin Laporte, who's actually now a faculty member at Paris Observatory. But anyway, the bottom line is ripples in the spinning saucer. Okay, let me see. Wait a second. I meant to, aha. Okay, so, no, that's not what I meant to do. Let me try this again. No, I will try this a different way. Just bear with me a minute. Okay, so, so we have the Sagittarius dwarf galaxy going around. We see these ripples in the spinning saucer, and you might say, oh, well then, maybe that's just by chance. We just happen to have Sagittarius hitting us right now. But actually, the last video that I want to show you is from another group that works more on the evolution of galaxies on larger scales. What you should be seeing coming up, if I haven't messed up, let's see. There we go. What you're seeing coming up is the evolution of a typical galaxy in one of their simulations. And what you should see is a typical galaxy is surrounded by these satellite galaxies. Let's play that one more time. It's the very end of their simulation. A typical galaxy is surrounded by these smaller satellite galaxies. So this would be the disk of our Milky Way. It's being bombarded constantly by these different satellites. And by the way, it's also giving as good as it gets. You can see these beautiful shells and streams. These are dead and dying galaxies. And indeed, around our Milky Way, you can see evidence. You can see the ghosts of long-dead galaxies surrounding our Milky Way. So the ripples in the Milky Way are really not that surprising and not that unusual. We just never had the data that was accurate enough until we had the European Space Agency satellite. I see a couple of questions. Yeah, great. So I would say I would call a galaxy dead when it's unable to form stars anymore. So once it's completely ripped apart and its stars and its dark matter are spread around everywhere, it's no longer capable of forming stars. You can actually also get, some galaxies are called red and dead for another lecture, but that just means they've run out of gas. They could still be a galaxy, but they're dead in the sense of not forming stars. But these galaxies are dead because they've been completely ripped apart. There's a question up here.
What would the impact of, let's say, numerous black holes in one galaxy? Would that just accentuate the ripple effect?
Yeah, that's a great question. What would happen if you had numerous black holes running into a galaxy? So yes, it depends on the size of the black hole, right? So there was a theory that dark matter was made entirely of 10 to the 6 black holes of a size of 1 million solar masses, 1 million times the mass of the sun. And I think that would, if that was true, that would gradually kind of make the galactic disk go from being very thin to make it thicker and thicker and thicker. So you've got the right intuition. We don't think dark matter is made that way, is made up of those things. I'm so close to the end of my talk class, sorry. Dismissed, no. I'll just finish this, then we'll go into questions. Okay, so let me just wrap up, because the last thing, I just don't want to forget to say this part, because I feel like, it's in particular at the moment, science feels very separate from you. But I would say, or maybe half of you are scientists and it's not so separate, I don't know. But I really call this Gaia, the Galaxy and You. That has had that title for 5 years or so, right? I really feel this is built on humanity. This is a frontier that we all own. A few of us may be the ones who are actually working on the Milky Way, but it's built on all of our ancestors' knowledge. It's built on all of our countries working together with humans across the planet, putting them together, thinking about Gaia's, the Gaia space satellite. So it's really a celebration of the human race. It's a celebration of our intellect, of our imagination, and our ingenuity. But it's really a celebration of society and civilization, that we support each other to be able to do this. And frankly, this science, my science, has been supported by your taxpayer dollars throughout my career. And that's true for scientists across the country. Now, just to be clear, that sounds like a political statement. It's just a true statement. I make that statement. I've been making it for 5 years every time I give this talk to say thank you to the American taxpayer. So let's celebrate ourselves and what we've done together. Okay, questions, and you get to start.
We have also, we're going to bring mics around, so up front.
Yeah. Great question. Okay, I'll repeat the question for now. What's the time scale of these things? So let's go back and think about it. That is a very scientific, you're a scientist, right? No, there we go. But you see, we're all scientists. We're all scientists. So here we go. So Sagittarius itself takes about 1 billion years to orbit the Milky Way. So the time scale that we're looking at over here is several billion years of evolution. And actually, the beautiful thing about running these simulations, right? We can't see the real universe, but because of human ingenuity built up over millennia, if you look at this, you can actually see, we said the sun goes around the galaxy in about 250 million years. So you can kind of see the disk. You can see the sun going round in 250 million years. And this part of the disk has gone round about 4 or 5 times, and that's when the satellite comes in. So the timescales all add up. Great question. Okay, yeah.
Well, now this
There's a mic coming. Let's do the mics.
But do you think we're the only humans out here?
Well, we might be the only humans, but for myself, I think there's got to be other people in the universe or other beings in the universe. Now, if you want someone to come and argue with you, I suggest you invite David Kipping, my colleague. He loves to give this talk about how we can prove that we are the only, well, not quite. But anyway, David Kipping, he actually works on planets, and so that's another suggestion for your talk series. Yeah. Oh, well, let's go over here, and we'll come back to the front. Yeah, there's a couple at the back. Let's do the back for a minute. There's one here, a gentleman here, and then one at the back. Yeah. Okay. Yeah, that's you. Oh. Okay.
My question is, why does at least in this kind of a galaxy, why is it on a plane in the first place?
Yeah, great question. So the answer to that question is pizzas. So if you think about a pizza, actually, I've never done this, but my understanding is you take a ball of pizza dough and you throw it up to make it go flat, right? And what's actually happening is the spinning force is flattening out the ball. And a similar thing is happening with the Milky Way. What we think has happened, now imagine the Milky Way ends up about this size, and I'm a big gas cloud that is going to make the Milky Way. And I'm mostly moving at random, but I have a very slight spin. Then as I collapse to make the Milky Way, conservation of angular momentum, that's the technical term, will increase the spin, and I would start spinning faster and faster. And that means if you start with something roughly spherical, you'll end up with something flattened. And in the middle, I said conservation of angular momentum, but you have all seen this, right? An ice skater. Now I'm an ice skater. I'm many things, right? I'm an ice skater. I bring my hands in. That's conservation of angular momentum. You know it. You have physical intuition for that. And that's the exact same physics that flattens pizzas. No, not quite. That's not conservation, right? That causes a galaxy to spin up, which in turn causes the flattening. Is that making sense? So like, you think astrophysics, it's really your everyday intuition, plus a little more, applied on very large scales. There was a question here and a question here. Let's start here and then go over there, and then work back to the front, at the back.
Great talk. Thank you so much.
You're welcome.
I have a question about the L2 Lagrange point where Gaia is.
Yes.
Is there a concern about potentially one day overcrowding L2?
Yeah, no, that's a great question. So L2, the Lagrange point, nice technical terms there. This is just the name for that very special place on the other side of the Earth from the sun, which is nice and stable dynamically. Currently, I'm not sure how much is there, but I think there's only Gaia and JWST. There might be other things that I don't know about. So currently, it's not a problem. I could imagine that becoming a problem in the future because it's a very special point in space. But I think the more pressing concern are those low Earth orbits currently, which are already becoming overcrowded with satellites. And I believe there are people working on that problem. Yeah. OK, so there was somebody else sort of towards the back here. Yes?
I have a related question. How is Gaia and the other thing sort of, what powers them? Because they're on the other side of,
yeah.
So there is no sun.
Yeah. No, so if we go back to Gaia, you can actually see here, you actually have to keep the instrument very, very cold. So this is a sun shield here, and this will always be pointed towards the sun, and that will be a set of solar arrays that will power the satellite. So all the satellites, I'm not much of a satellite expert, but my understanding is they're all have a given lifetime, and they try to make things last a certain lifetime. And after a while, for instance, in lower Earth orbits, you have a little bit of fuel for maneuvering that's used occasionally, and that might run out. Or we have other satellites where parts of them have broken, and we haven't been able to use them again. We have some satellites where parts of them have broken. The Kepler mission, for instance, which you may have heard of, they discovered a lot of planets. So it had part of it break, and it ended up spinning wildly. And what we did was we changed our analysis routine to take that into account, which is really fun. Unfortunately, in the terms of Gaia, I have to say that it's officially shut down. I think it's already officially shut down. The Europeans have shut it down, and we've taken all the data we will take with it. Anyway, that was a long answer to your question. So some of the power is going to come from solar panels, which are also protecting it from the sun. OK, question here. And we have to get back to you.
Regarding the rippling effect.
Yes.
We actually made pizza last night. and I can assure you that the mass of this thing is not evenly distributed. So in a galaxy, if the mass is not evenly distributed, would that have an effect on the rippling?
Yeah, yeah. Well, so I think, I hate to disparage your pizza making skills, but I think that with the age of the universe and the beauty of gravity, that will tend to smooth out the ripples at some level, but not entirely. Otherwise, we wouldn't form stars. So within the disk, you have clouds of gas that are continuously collapsing and forming stars. So you can think of that next time you have little lumps in the pizza. And there are also the spiral arms as well, which is a different gravitational effect. Am I answering your question? If there's a, at the center of, this is fun, at the center of the Andromeda galaxy, we do see an asymmetry, the very center. We see a bright spot, which is orbiting the very center, and that has to do with the presence of a supermassive black hole. That's kind of fun. And we also see, in some galaxies, you will see on the outskirts warps, which means this side is going down and this side is going up. So it's not that it's a beautiful, like I was being cruel. Your pizza dough is just fine. Yes. OK, question here. Yeah, can you use the mic, actually? Now it's got that.
How far out was Gaia actually able to go?
To actually see in space? Yeah, yeah. So the way satellites work is we call it a magnitude limit, but it's effectively just a brightness limit. So there's a limit to how faint it can see stars. So what that means is, effectively, there are some very luminous stars that it can see a really long way away. So that would be at about 3 times the width of the disk of the galaxy. It could see out into space surrounding our galaxy. That was how it was able to see the Sagittarius streams, right? But that's about the limit, because those were really luminous stars that it was seeing right at the edge of its limit on how faint it could detect things. Is that making sense? Yeah, OK. There was a question here.
Is the Sagittarius dwarf galaxy the only one that they've seen?
No, no, no. So actually, the question was, is the Sagittarius dwarf galaxy the only one we've seen? So when I started graduate school, which was back in 1990, this was just before the discovery of satellites, of Sagittarius. There were 11 known satellite galaxies of the Milky Way. Sagittarius makes 12. We now know of over 50. And a lot of those have been discovered there was a big bump about a decade ago, and then there's been another bump in recent years. So it's really just bumping up. It's just getting a lot. It's really exciting. The question here.
2 questions. What creates the energy for the spinning of the galaxy? And isn't gravity space-time?
Yeah. So the spinning of the galaxy, as I said, is really to do with the spin-up is the conservation of angular momentum. So you start with a certain amount of angular momentum. Yeah, great question. That's an existence problem. So the thought is, early on in the universe, we think there are slightly overdense regions and slightly less overdense regions. We have evidence for the size of those fluctuations by looking at something called the cosmic microwave background radiation. But the point is, they start as like tiny different overdensities and underdensities. Gravity will tend to amplify those. And once you have different lumps growing, Now they're interacting, and they don't always interact exactly symmetrically. So a tiny amount of angular momentum gets spread out at random. And then when you collapse, that gets amplified. It kind of makes sense. Yeah, you're nodding. I've convinced you, right? But the second part of your question, yes. OK, so yes, Newton came up with Einstein's theory of general relativity. No, Newton came up with the law of gravity to describe interactions between massive objects. And I want to just take a minute. Science is just a description. It's not truth. We're just trying to describe the universe, right? It's us trying to describe the universe better and better and better. So Newton comes up with the law of gravity, which does a really fantastic job of describing our experience of an apple falling from the tree and the planets going around the sun, for example. And that's terrific, except for Mercury. He can't explain Mercury. Mercury's orbit deviates from what his description of gravity tells us. So Einstein comes along in the early 20th century, and he updates our description of gravity to his general theory of relativity. And that's your reference there. Gravity and space-time, they're all tied together in Einstein's theory of general relativity. So general relativity is an update to our theory of gravity. So I actually can get away with using Newton's law of gravity for much of my own work. It's in more intense gravitational fields, the orbit of Mercury. If we start talking about black holes, then you have to use the more advanced theory of gravity. Okay.
Can I try to get a few more in the back? We only have a little bit more time.
Okay.
But let me see. Who back here? I don't want to miss you. Here.
It's kind of a double question. One thing is, how does Gaia measure the distance to the sun? And also, you talked earlier about the light of the stars, how far out it could get. How do we know if the stars are bright or which one?
Yeah, the second question would be a really long answer. The first one is great because it's a class participation one. And we might end up spending so long we just end on this, but that would be good because everybody participates. OK, so everybody, you've got to hold your finger at arm's length. Stretch your finger out. Right. Now put your hand in front of one eye, and then your hand in front of your eye. Look at what appears to be behind your finger as you change, right? It changes, right? Now, put your finger here. Right. Remember what right, you should see your finger jump. It's magic. It's a change of perspective, right? Now put your finger here. And notice what happens when your finger is closer. A bigger apparent change in perspective. This is what Gaia is doing, right? It's amazing, right? So Gaia is next to the Earth. The Earth goes around the sun. So that means Gaia's view on the universe and our view on the universe changes every 6 months. Well, changes all the time, but it's a big difference in perspective over 6 months. And Gaia uses that to measure distances to stars. Okay, so this is like Earth in June, Earth in January. Is that 6 months? Maybe it's 5 months. And Earth in June, Earth in January, right? This is like a nearby star, and those are distant stars. The stars with big apparent shifts are very close. The stars with tiny apparent shifts are far away. And it's a pattern that repeats every 6 months, so the measurement gets better and better and better. So this is actually something pure. This is mathematics. It's geometry. It's just, this is truth, if you want to say it that way. The effect is called parallax. Okay? You experience it all the time. Again, we're just taking something simple from the Earth, learning about the universe. I think that's a great place to stop. I'm sorry, people. But thank you.